Welcome to tonight's journey through the fascinating world of food science. As you settle in and prepare for rest, we'll explore the hidden secrets behind the foods we eat every day. Food is more than just sustenance. It's a complex interplay of chemistry, physics, biology, and culture that humans have been perfecting for thousands of years. Our understanding of food chemistry has revolutionized cooking in ways our ancestors could never have imagined. What was once done by tradition and intuition is now understood at the molecular level. This knowledge hasn't replaced the art of cooking, but rather enhanced it, giving chefs new tools to create extraordinary culinary experiences. From the precision of molecular gastronomy to the time-tested techniques of fermentation, science has unveiled why these methods work and how we can perfect them. But perhaps most fascinating is how food engages us beyond just taste. While your tongue might detect sweetness in a fresh strawberry, it's actually your nose that identifies the fruity aroma, your eyes that appreciate its vibrant red color, your fingers that feel its delicate texture, and even your ears that register the subtle crunch as you bite into it. Tonight, we'll explore how all your senses contribute to the complex experience we call flavor, and how scientists are still discovering new ways that food interacts with our bodies and minds. Let's begin our gentle exploration into the science that transforms ingredients into the meals that nourish us, comfort us, and bring us together. The chemistry behind flavor, how we taste and why we like what we like. Our journey begins with the fundamental building blocks of how we experience food, the 5 basic tastes that your tongue can detect: sweet, salty, sour, bitter, and umami. Each of these taste sensations evolved for specific biological purposes. Sweetness helped our ancestors identify energy-rich carbohydrates. Saltiness ensured we consumed essential minerals. Sourness warned us of potentially spoiled foods. Bitterness served as a natural alarm system for many toxic compounds in plants. And umami, that rich, savory quality, signaled the presence of protein-rich foods. Umami stands apart as a fascinating chapter in food science history. While the other 4 tastes were recognized for centuries, umami wasn't scientifically identified until 1908 by Japanese chemist Kikunae Ikeda. While studying the distinctive flavor of dashi, a soup stock made with kombu seaweed, Ikeda isolated glutamic acid and recognized it produced a taste that couldn't be classified within the existing 4 categories. He named this 5th taste umami, from the Japanese word for delicious. Despite his discovery, Western science was reluctant to accept umami as a distinct taste until the 1980s, when receptors specifically responding to glutamates were finally identified on the human tongue. As we cook, thousands of chemical reactions transform the flavor compounds in our ingredients. Raw foods contain precursor molecules that, when exposed to heat, undergo remarkable changes. A raw potato contains mainly starch and has little aroma, but as it cooks, hundreds of new compounds form, creating the characteristic flavor we recognize. Similarly, raw meat offers a metallic, blood-like taste, while cooked meat develops complex savory notes through various chemical reactions. Perhaps the most significant of these reactions is the Maillard reaction, named after the French chemist Louis Maillard, who first described it in 1912. This isn't just one reaction, but a whole cascade of chemical changes that occurs when proteins and sugars are heated together above 285 degrees Fahrenheit or 140 degrees Celsius. The Maillard reaction is responsible for the browned surface of seared steak, the complex flavors of roasted coffee beans, the golden crust of bread, and the distinctive taste of maple syrup. As amino acids, the building blocks of proteins, react with reducing sugars, they create hundreds of new flavor and aroma compounds. Scientists have identified over 1,000 different molecules produced by the Maillard reaction in foods. Related but distinct from the Maillard reaction is caramelization, which involves only sugars breaking down under heat without proteins involved. When sugar molecules reach approximately 320 degrees Fahrenheit, 160 degrees Celsius, they begin to fragment and reform into new compounds. A single type of sugar can transform into over 100 different molecules through caramelization, creating complex flavors ranging from buttery and milky to nutty and slightly bitter. This is why caramel isn't just sweet, it has depth and complexity that simple sugar doesn't possess. Salt plays a particularly fascinating role in flavor enhancement that goes far beyond simply making food taste salty. When sodium ions from salt interact with our taste receptors, they actually amplify our perception of other flavors. Salt suppresses bitterness, which can mask more desirable flavors, while enhancing sweetness and umami. This is why a small pinch of salt in cookie dough or chocolate makes the dessert taste sweeter, not saltier. Salt also releases certain molecules from foods, making them more volatile and therefore more readily detected by our sense of smell, further enhancing flavor perception. The chemical compatibility of ingredients explains why certain food pairings work so well together. The food pairing theory suggests that foods that share key flavor compounds will complement each other. This explains classic combinations like tomatoes and basil, which share several flavor compounds, including linalool and eugenol. Similarly, chocolate and coffee share nearly 600 flavor compounds, explaining their natural affinity. However, some cuisines, like Indian cooking, often pair ingredients with contrasting rather than similar compounds, creating harmonious dishes through flavor opposition rather than similarity. Not everyone experiences these flavors the same way. Genetic variations create significant differences in taste perception among individuals. About 25% of people are super tasters, born with a higher density of taste buds and particular sensitivity to bitter compounds. These individuals often find dark chocolate overwhelmingly bitter, cruciferous vegetables like broccoli unpleasantly intense, and spicy foods intolerable. On the other end of the spectrum, non-tasters have fewer taste receptors and may seek out more intensely flavored foods to achieve satisfaction. One particular gene, TAS2R38, determines whether you can taste certain bitter compounds, like PTC, which is structurally similar to compounds in Brussels sprouts and cabbage. Finally, let's address one of food science's most persistent controversies, MSG, or monosodium glutamate. This ingredient has been unfairly maligned despite overwhelming scientific evidence of its safety. MSG is simply the sodium salt of glutamic acid, the same amino acid that creates umami flavor naturally in foods like tomatoes, Parmesan cheese, and mushrooms. The Chinese restaurant syndrome, reported in a 1968 letter to the New England Journal of Medicine, spawned decades of MSG avoidance, despite the fact that subsequent double-blind studies have repeatedly failed to demonstrate that MSG causes headaches or other symptoms in most people. The FDA and regulatory bodies worldwide classify MSG as generally recognized as safe. The misconception about MSG reflects how cultural biases and misconceptions can sometimes override scientific evidence in our food choices. The physics of cooking, how heat and energy transform our food. The way we apply heat to food dramatically influences its final texture, flavor, and appearance. This process involves three distinct methods of heat transfer: conduction, convection, and radiation. Conduction occurs when heat moves directly between objects in contact, like a steak on a hot pan. Convection involves heat transfer through a moving liquid or gas, such as in boiling water or a convection oven. Radiation transfers heat through electromagnetic waves, as in microwave cooking or broiling. The materials we cook with significantly impact heat distribution. Copper pans, prized by professional chefs, conduct heat about 20 times more efficiently than stainless steel, allowing for precise temperature control and even cooking. Cast iron, on the other hand, heats slowly but retains heat exceptionally well, making it ideal for maintaining consistent temperatures during longer cooking processes. The thickness of cookware also matters. Thicker pans distribute heat more evenly and reduce hotspots that can cause burning. Pressure cookers represent a fascinating application of physical principles. By sealing in steam, these devices increase the pressure inside the cooking chamber, which raises the boiling point of water. At sea level, water boils at 212 degrees Fahrenheit, 100 degrees Celsius, but inside a pressure cooker, it can reach up to 250 degrees Fahrenheit, 121 degrees Celsius. This higher temperature dramatically accelerates cooking by increasing the energy transfer to the food. However, at high altitudes where atmospheric pressure is already lower, the physics work differently. In Denver, Colorado, for example, water boils at just 203 degrees Fahrenheit, 95 degrees Celsius, making cooking slower. Pressure cookers are particularly valuable in these environments as they compensate for the lower atmospheric pressure. Microwave ovens work through an entirely different physical principle. Rather than applying external heat, they use electromagnetic radiation at a specific frequency, 2.45 gigahertz, that excites water molecules in food, causing them to rotate rapidly and generate heat through friction. This explains why foods with higher water content heat more quickly in microwaves, and why microwaves heat food from the inside out, wherever water molecules exist. However, this is also why microwaves heat unevenly. The standing waves created inside the oven form patterns of high and low energy, which is why most microwaves include turntables to promote more even heating. The difference between microwave-safe and non-microwave-safe containers relates directly to how materials interact with electromagnetic waves. Microwave-safe containers don't absorb significant microwave energy themselves, allowing the waves to pass through to the food. Materials containing water, like some ceramics or certain metals, can absorb microwave energy, potentially reaching dangerous temperatures or causing arcing. This is why metal is generally avoided in microwaves. The electric fields in the microwave induce currents in metal objects, which can concentrate at sharp edges and create sparks. When cooking meat, the physics of heat transfer explains why letting it rest after cooking improves its texture and juiciness. During cooking, heat causes muscle fibers to contract and push moisture toward the center of the meat. If cut immediately after cooking, this moisture, which hasn't had time to redistribute, flows out, resulting in dry meat. Resting allows time for this pressure to equalize and moisture to redistribute throughout the meat. For larger cuts like roasts, this resting period can improve moisture retention by up to 15%. Achieving the perfect crust involves complex physical transformations at the surface of foods. When heat dehydrates the outer layer of bread, steak, or fried foods, it creates a moisture gradient. Water evaporating from the surface carries away heat energy, keeping the temperature at the surface around 212 degrees Fahrenheit, 100 degrees Celsius, until most of the surface moisture is gone. Only then can the temperature rise high enough for Maillard reactions and caramelization to occur, developing the complex flavors and crispy textures we crave. This is why patting foods dry before searing is so effective. It allows the surface to quickly surpass the temperature threshold needed for browning. Emulsions represent a fascinating application of food physics. Oil and water naturally repel each other due to their different molecular structures. Water molecules are polar, having positive and negative ends, while oil molecules are non-polar. When you shake oil and vinegar together, they temporarily mix but quickly separate. Emulsifiers like egg yolks in mayonnaise or mustard in vinaigrette contain molecules with both polar and non-polar parts. These molecules act as mediators, with their water-loving ends facing the water and their oil-loving ends facing the oil, creating a bridge that stabilizes the mixture. This is why adding a small amount of mustard to a vinaigrette can keep it from separating for hours instead of minutes. The science behind the perfect crispy coating on fried foods involves multiple physical processes. When food enters hot oil, ideally between 350 to 375 degrees Fahrenheit or 175 to 190 degrees Celsius, the surface moisture rapidly evaporates, creating a dehydrated outer layer. This layer acts as a barrier, preventing oil from saturating the food while allowing internal moisture to steam the interior. The ideal coating, like a batter or breading, contains starch molecules that undergo rapid gelatinization and dehydration in the hot oil, creating a rigid network that contributes to crispness. Temperature control is crucial. If the oil is too cool, the food absorbs more oil before the protective crust forms. If too hot, the exterior burns before the interior cooks. Food preservation secrets. How we make food last longer. Throughout human history, preserving food has been crucial for survival. Two of the oldest methods, using salt and sugar, work on similar principles. Both create environments with high osmotic pressure, drawing water out of microbial cells through osmosis. When bacteria and fungi lose their cellular water, their metabolic processes and reproduction are inhibited. This is why honey and jam, high in sugar, and salted meats and fish can last for extended periods without refrigeration. Salt has the added benefit of being directly toxic to many microorganisms that cause food spoilage. Fermentation represents one of the most fascinating preservation methods. What seems counterintuitive, deliberately allowing certain microorganisms to grow in food, actually prevents spoilage. In foods like kimchi, sauerkraut, and pickles, beneficial bacteria, primarily lactobacillus species, convert sugars into lactic acid. This acidification creates an environment too hostile for spoilage organisms and pathogens. The pH of properly fermented sauerkraut, for example, drops to around 3.5, well below the threshold at which many harmful bacteria can survive. Additionally, these beneficial bacteria can produce bacteriocins, natural compounds that directly inhibit other bacterial species. Honey deserves special mention as perhaps nature's perfect preserved food. Archaeological findings have discovered edible honey in ancient Egyptian tombs over 3,000 years old. This remarkable shelf stability comes from multiple preservation factors working together. Honey's extremely low moisture content, typically below 18%, creates high osmotic pressure. Its natural acidity, pH between 3.2 and 4.5, inhibits many microorganisms. Additionally, honey contains the enzyme glucose oxidase, which produces hydrogen peroxide, a natural antimicrobial. Some honey varieties also contain plant-derived compounds with additional antimicrobial properties. This combination of preservation mechanisms makes honey one of the only foods that, when properly stored, never spoils. Freeze-drying represents a relatively modern preservation technique that maintains flavor better than many other methods. This process involves freezing food and then removing the ice through sublimation, the direct transition from solid to gas without passing through a liquid state. This occurs in a vacuum chamber where pressure is reduced to below the triple point of water. Since no liquid water forms during the process, cellular structures remain largely intact and most flavor compounds are preserved. Without water, enzymatic and microbial activities that cause spoilage cannot occur. This is why freeze-dried fruits retain their vibrant flavors and colors, and why freeze-dried coffee preserves more aromatic compounds than spray-dried instant coffee. The science of canning involves creating a hermetically sealed, oxygen-free environment after destroying all microorganisms present in the food. When cans or jars are heated to temperatures between 240 to 250 degrees Fahrenheit, 116 to 121 degrees Celsius, typically under pressure, heat-resistant bacterial spores like those from Clostridium botulinum are destroyed. As the containers cool, a vacuum forms inside, pulling the lid tight and preventing recontamination. This vacuum seal is why unopened canned foods can remain safe for years or even decades. The distinctive pop sound when opening a jar of preserves indicates this vacuum seal has been maintained. The effectiveness of drying as a preservation method relates directly to water activity, a concept that measures water available for microbial growth rather than total moisture content. Most bacteria cannot grow at water activity levels below 0.91, and most molds stop growing below 0.70. Properly dried foods typically have water activity levels between 0.10 and 0.60, well below the threshold for microbial growth. This is why dried foods like jerky, dried pasta, and dehydrated spices have remarkable shelf stability despite being stored at room temperature. Vinegar preservation works through acidification. With a pH typically between 2.0 and 3.0, vinegar creates an environment too acidic for most bacteria to survive. Additionally, acetic acid, the main component of vinegar, can penetrate bacterial cell membranes and disrupt their internal pH, further inhibiting growth. Traditional pickled vegetables, preserved in solutions containing 2 to 5% acetic acid, demonstrate how this simple compound has been used as an effective food preservative for thousands of years across virtually all cultures. Traditional food preservation methods across cultures reveal remarkable scientific intuition developed long before formal scientific understanding. Icelandic hakal, fermented shark, Scandinavian lutefisk, lye-treated fish, and Asian century eggs, alkali preserved eggs, all use alkaline environments to create preservation effects. South American charqui, a form of jerky, employs altitude and sun exposure for rapid dehydration. These methods, developed through generations of observation and refinement, represent sophisticated applications of preservation principles, tailored to local environments and available resources. Modern food preservatives often mimic natural preservation mechanisms. Sodium benzoate, commonly used in acidic foods like sodas and salad dressings, works similarly to the benzoic acid naturally found in cranberries and plums. Citric acid, used as both a flavor enhancer and preservative, is identical to the compound abundant in citrus fruits. Even nitrates and nitrites, controversial preservatives used in cured meats, occur naturally in vegetables like celery and spinach. Understanding these connections helps explain why many artificial preservatives are chemically identical or similar to compounds that have preserved foods in nature for millennia. Storage science: the best ways to keep food fresh. Tomatoes exemplify how understanding cellular biology impacts proper food storage. When stored below 55 degrees Fahrenheit or 13 degrees Celsius, tomatoes activate genes that shut down ripening processes and flavor development. Additionally, cold temperatures damage the delicate membranes within tomato cells that separate enzymes from their substrates. When these membranes break down, it leads to a mealy texture and diminished flavor. This is why refrigerated tomatoes often taste bland compared to those stored at room temperature. The exception is fully ripe tomatoes, which can be refrigerated briefly to extend their usable life before they spoil. The ethylene gas phenomenon represents a fascinating aspect of fruit and vegetable storage. Ethylene, C2H4, is a plant hormone that triggers ripening, and some fruits, including apples, bananas, avocados, and pears, produce it in substantial quantities. When these ethylene producers are stored alongside ethylene-sensitive produce like broccoli, leafy greens, or cucumbers, they accelerate ripening and potentially cause premature spoilage. A single ripe banana can significantly increase the ripening rate of nearby produce. This is why separating these items can extend shelf life, while strategically placing them together can speed ripening of firm fruits when desired. The recommendation to store onions and potatoes separately has sound scientific backing. Onions release ethylene gas and volatile sulfur compounds that potatoes absorb, causing them to sprout eyes and spoil faster. Additionally, potatoes release moisture and gases that can cause onions to soften and develop mold. The ideal storage conditions for these staples also differ. Onions prefer cooler, drier environments with good air circulation, while potatoes do best in cool, slightly more humid conditions with minimal light exposure to prevent greening, which indicates the formation of potentially toxic solanine. Different vegetables require specific humidity levels for optimal storage. Leafy greens and most thin-skinned vegetables like cucumber and bell peppers require high humidity, 95 to 98%, to prevent wilting through water loss. Root vegetables do best at medium-high humidity, 85 to 95%. Onions, garlic, and winter squash preserve longest at lower humidity levels, 60 to 70%, which prevent mold growth while maintaining internal moisture. Modern refrigerators often include humidity-controlled drawers to accommodate these differences, typically labeled as crisper, high humidity, and fruit, Lower humidity compartments. Cheese storage involves balancing moisture retention while allowing the cheese to breathe. Semi-soft and hard cheeses develop ammonia and other compounds as part of their natural aging process. When wrapped in plastic, these gases can't escape, potentially altering the cheese's flavor profile and encouraging undesirable mold growth. Specialized cheese paper or parchment paper offers an ideal compromise, providing enough moisture protection while allowing gas exchange. Blue cheeses particularly benefit from this breathing room, as their characteristic flavors develop through controlled exposure to oxygen. Light exposure dramatically impacts olive oil quality. Ultraviolet light triggers photooxidation reactions that break down the polyphenols and oleocanthal compounds responsible for olive oil's health benefits and distinctive peppery flavor. Studies have shown that exposure to light for just 2 weeks can reduce polyphenol content by up to 40%. Additionally, light exposure accelerates the oxidation process that leads to rancidity. This is why quality olive oils are typically sold in dark glass or opaque containers, and why storing them in a dark cupboard rather than on the counter near the stove preserves their flavor and nutritional profiles significantly longer. The freezability of foods relates directly to their cellular structure and water content. Foods with high water content and delicate cell structures, like lettuce and cucumber, become mushy when frozen because ice crystals rupture their cell walls. Eggs in shells crack when frozen as water expands. However, many foods freeze surprisingly well. Bell peppers, berries, bananas, peeled, and even avocados can be frozen successfully. The key difference lies in how their cellular structures respond to ice crystal formation and whether their texture relies on cellular integrity. Blanching vegetables before freezing helps by deactivating enzymes that would otherwise cause flavor deterioration during storage. Honey crystallization is a natural physical process rather than spoilage. All honey eventually crystallizes as its supersaturated glucose solution seeks equilibrium. The glucose molecules bond to microscopic particles in honey, like pollen grains, and form crystals, while fructose remains liquid. The ratio of glucose to fructose determines crystallization speed. Higher glucose honey like clover crystallizes more quickly than high fructose varieties like Tupelo. Temperature also plays a crucial role. Crystallization occurs most rapidly between 50 to 59 degrees Fahrenheit and 10 to 15 degrees Celsius and slows both above and below this range. Gentle warming under 104 degrees Fahrenheit or 40 degrees Celsius to preserve beneficial compounds redissolves these crystals by providing energy for the glucose molecules to break their crystalline bonds and return to solution. Coffee storage science focuses on protecting volatile aromatic compounds. After roasting, coffee contains over 800 volatile compounds that contribute to its complex flavor and aroma. These compounds escape readily at room temperature and oxidize when exposed to oxygen, moisture, heat, and light. Studies show that ground coffee loses 60% of its aromatics within 15 minutes of grinding. Whole beans stored in an airtight container away from light maintain their quality up to 4 times longer than pre-ground coffee. The refrigerator, while seeming logical, creates problems through condensation that forms when cold beans are repeatedly exposed to warm air, introducing damaging moisture. This is why specialty coffee is typically recommended to be stored in opaque, airtight containers at room temperature and ground just before brewing. Baking chemistry, the science of perfect baked goods. The protein structure of gluten represents one of baking's most fundamental scientific concepts. When flour proteins glutenin and gliadin absorb water, they form gluten, an elastic network that can stretch and trap gas bubbles. The mechanical action of kneading aligns these proteins, creating stronger bonds and more organized structures. At the molecular level, this process involves breaking and reforming disulfide bonds between protein chains. Different wheat varieties contain varying amounts of these proteins. Bread flour contains 12 to 14% protein for strong gluten development, while cake flour contains just 7 to 9% protein for tender results. This difference explains why substituting one for the other dramatically affects texture. The distinction between kneading bread dough and minimally mixing cake batter directly relates to gluten development. Bread benefits from strong gluten networks that can trap carbon dioxide, allowing dramatic rise and creating desired chewiness. Extensive kneading encourages these protein structures to develop. In contrast, cakes rely on tenderness and fine crumb structure. Overmixing cake batter develops too much gluten, resulting in tough, tunneled textures rather than tender ones. This is why cake recipes often specify mix just until combined, while bread recipes call for several minutes of vigorous kneading. Leavening agents work through distinct chemical principles. Yeast, a living organism, produces carbon dioxide through fermentation of sugars, along with ethanol and over 500 flavor compounds. Baking soda, sodium bicarbonate, requires acid to react and release carbon dioxide. This is why recipes using baking soda include acidic ingredients like buttermilk, yogurt, or chocolate. Baking powder contains both the alkali, sodium bicarbonate, and acid, typically cream of tartar, in dry form, which react when moistened. Double-acting baking powder includes two acids with different activation temperatures, providing initial leavening when mixed with liquid and additional leavening when heated, ensuring maximum rise. Eggs perform multiple functions in baking through their unique protein and lipid structures. Egg whites, composed of approximately 90% water and 10% proteins, can trap air when whipped because these proteins unfold, denature, and form stable films around air bubbles. This structure provides leavening in angel food cakes and soufflés. Egg yolks contain emulsifiers, primarily lecithin, which help combine ingredients that would normally separate, like fat and water in cake batters. The proteins in whole eggs coagulate when heated, providing structure and stability. Additionally, eggs contribute moisture, flavor compounds, color, and nutritional value, making them remarkably multifunctional ingredients. The Maillard reaction manifests differently in baking than in cooking. In baking, this reaction typically occurs at the food surface, where temperatures are highest and dehydration occurs most rapidly. The darker, drier exterior of bread crust develops through Maillard reactions, while the interior remains light-colored because its temperature stays at or below 212 degrees Fahrenheit, 100 degrees Celsius, due to moisture content. This reaction is affected not just by temperature, but also by pH. Alkaline environments accelerate browning, which is why pretzels dipped in lye solution or baking soda, a milder alkali, develop their characteristic mahogany color. The type of sugar present also influences browning. Recipes with more glucose and fructose, like honey, brown faster than those made with sucrose. Altitude significantly affects baking through reduced atmospheric pressure. At 5,000 feet, 1,524 meters, water boils at approximately 203 degrees Fahrenheit, 95 degrees Celsius, rather than 212 degrees Fahrenheit, 100 degrees Celsius. This lower boiling point means moisture evaporates more quickly, leavening gases expand more rapidly, and proteins set faster. These changes cause multiple issues: excessive rising followed by collapse, dry textures, and coarser crumb structure. Successful high-altitude baking typically requires increased liquid to counter faster evaporation, decreased leavening to prevent overexpansion, higher flour amounts for structural support, and higher baking temperatures to set structure before collapse. These adjustments demonstrate how baking recipes represent balanced chemical formulas that must account for environmental conditions. Flaky pastry relies on distinct layers of fat and dough. When solid fat, typically butter, is incorporated into dough as discrete pieces rather than fully mixed in, it creates separate layers. During baking, these fat layers melt, creating space between the dough layers. Simultaneously, the water in the butter converts to steam, further separating these layers and creating the characteristic flakiness. The temperature control is crucial. Keeping ingredients cold prevents the fat from blending completely into the dough. This also explains why overworking pastry dough destroys flakiness. The friction generates heat that melts fat prematurely, eliminating the distinct layers needed for flaky results. Ingredient temperature dramatically affects baking outcomes by influencing chemical reaction rates and physical properties. Cold ingredients slow gluten development and enzyme activity while maintaining fat structure. Cold butter in cookie dough, for instance, takes longer to melt during baking, limiting spread and creating thicker cookies. Conversely, room temperature ingredients incorporate more easily, trapping more air during mixing. This is particularly important with the creaming method, where butter and sugar beaten together need to be at 65 to 70 degrees Fahrenheit, 18 to 21 degrees Celsius, soft enough to trap air but firm enough to maintain structure. These temperature effects explain why identical recipes can produce dramatically different results based solely on ingredient temperature. The science behind chilled cookie dough reveals multiple chemical processes. During resting, enzymes break down some starches into simpler sugars, enhancing sweetness and browning potential. The flour proteins gradually absorb moisture, becoming fully hydrated and limiting spread during baking. Flavors meld as volatile compounds distribute throughout the dough, creating more complex taste profiles. Research has shown that cookies from dough chilled for 24 to 36 hours develop deeper caramelization, more varied texture with crisp edges and soft centers, and more complex flavor profiles than those baked immediately after mixing. This time-dependent transformation explains why many professional bakers insist on this resting period. Caramelization of sugars in baking follows a complex pathway of chemical reactions. When heated above their melting point, 320 degrees Fahrenheit or 160 degrees Celsius for sucrose, sugar molecules break apart and reform into hundreds of new compounds. The process follows several stages. First, sugar melts into a clear syrup, then it begins to yellow as compounds like caramelin form. Next, it darkens to amber as caramelin and caramelin develop. Finally, it reaches dark brown as bitter compounds like caramelin emerge. Each stage contributes different flavor compounds. Early caramelization produces buttery, vanilla notes, while later stages add coffee-like bitterness. Understanding this progression allows bakers to stop the process at the desired flavor profile, whether making delicate caramel sauce or robust caramel for bittersweet flavor applications. The science of taste perception, how we experience food beyond our taste buds. Our experience of flavor is predominantly determined by our sense of smell rather than taste. While taste buds can only detect 5 basic tastes, our olfactory system can distinguish thousands of different aroma compounds. When we eat, volatile compounds from food travel from the back of the throat to olfactory receptors high in the nasal cavity, a process called retronasal olfaction. This explains why pinching your nose while eating chocolate reduces your perception to merely sweet rather than the complex chocolate flavor, which depends on over 600 aromatic compounds detected by smell. Research indicates that up to 80% of what we call flavor actually comes from aroma rather than taste. The connection between smell and flavor becomes strikingly apparent during respiratory infections. When the olfactory epithelium, the tissue containing smell receptors, becomes inflamed, or when mucus blocks odorants from reaching these receptors, our ability to perceive food flavors diminishes dramatically. What many people describe as losing taste during a cold is predominantly a loss of smell function. This sensory limitation explains why foods often seem bland or one-dimensional during illness. The phenomenon is so significant that temporary anosmia, smell loss, has been used in research to demonstrate how central olfaction is to the dining experience. Subjects typically report 50 to 80% reduced flavor perception even when taste function remains intact. Taste aversions and preferences have both evolutionary and experiential foundations. Evolutionary psychologists point to our innate preference for sweetness, signaling calorie-rich foods, and aversion to bitterness, potentially signaling toxins, as survival adaptations. However, food preferences are also heavily influenced by exposure, particularly during childhood and periods of neural plasticity. Foods encountered positively during these periods often become lifelong preferences. Interestingly, taste aversions can form after just a single negative experience, particularly if nausea follows consumption, through a learning mechanism called conditioned taste aversion. This powerful association can last decades and required only one negative experience, unlike most other forms of learning that require repetition. Children's heightened sensitivity to bitter flavors has sound evolutionary logic. Young omnivores exploring their environment face higher risks from potential toxins, many of which taste bitter. Research shows that children have both more taste buds and greater sensitivity to bitter compounds than adults. This sensitivity typically decreases during adolescence and adulthood, a process called taste moderation. This explains why foods like coffee, dark chocolate, and bitter vegetables that many adults enjoy are often rejected by children. Cultural practices, like adding sugar to bitter foods for children, as in sweetened cocoa or glazed vegetables, may serve as training wheels for gradually accepting these flavors. Spicy foods present a fascinating sensory paradox. The burning sensation from chili peppers isn't a taste at all, but rather a form of chemesthesis, chemical stimulation of pain and temperature receptors. Capsaicin, the active compound in chilies, activates TRPV1 pain receptors, normally responsible for detecting heat above 109 degrees Fahrenheit, 43 degrees Celsius. These same receptors are triggered by actual heat, which explains why the sensation feels like thermal burning despite no actual temperature increase. The body responds by releasing endorphins, creating a mild analgesic effect and sense of euphoria. This pain-pleasure cycle helps explain why spicy food preferences show high cultural variation compared to basic tastes, like sweetness, which have more universal appeal. Genetic factors create significant differences in flavor perception between individuals. The most well-studied example involves PTC, phenylthiocarbamide, and related compounds like PROP, 6N-propylthiouracil, which taste intensely bitter to some people but nearly flavorless to others. This variation is determined primarily by the TAS2R38 gene. Supertasters not only detect these specific compounds, but generally have more fungiform papillae, structures containing taste buds, on their tongues, making them more sensitive to most flavors. Other genetic variations affect preferences for cilantro, perceived as soap-like by approximately 14% of people due to OR6A2 gene variations, perception of specific artificial sweeteners, and sensitivity to fat texture. These differences remind us that no two people experience the same dish in exactly the same way. Food cravings involve complex neuroscience beyond simple hunger. When we crave specific foods, our brain's reward centers, particularly the nucleus accumbens and the ventral tegmental area, become activated. These regions release dopamine, the neurotransmitter associated with pleasure and anticipation. Functional MRI studies show that simply viewing images of highly desirable foods activates these same brain regions. Interestingly, specific cravings often correlate with nutritional needs, protein, salt, or particular vitamins, emotional states, hormonal fluctuations, or habitual patterns. The persistent power of food cravings relates to how deeply food preferences are encoded in our memory and reward systems, connections formed from our earliest eating experiences. Airplane cabin pressure creates a unique environment that significantly alters taste perception. At typical cruising altitudes, cabin pressure is equivalent to approximately 8,000 feet, 2,438 meters above sea level. This lower pressure reduces oxygen saturation in blood by about 5 to 10%, which impacts how taste and smell receptors function. Additionally, the extremely dry air, usually below 20% humidity compared to 30 to 60% on the ground, dries out nasal passages, further reducing aroma detection. Studies conducted by airline caterers show that at altitude, our perception of sweetness decreases by about 15 to 20% and saltiness by 20 to 30%. Umami appears more resistant to these effects, explaining why tomato juice and savory foods are particularly popular in-flight choices. Airlines have gradually reformulated their menus to accommodate these perceptual shifts, often increasing salt and sugar content by 20 to 30% compared to the same dishes served on the ground. Some carriers have also begun incorporating more umami-rich ingredients like mushrooms, aged cheeses, and fermented foods to enhance flavor perception at altitude. Menthol creates its characteristic cooling sensation through a fascinating sensory illusion rather than by actually lowering temperature. When menthol compounds from mint or synthetic sources contact the skin or mucous membranes, they bind to TRPM8 receptors, the same cold-sensing ion channels that normally detect actual drops in temperature. This activation tricks the brain into perceiving cold where none exists, similar to how capsaicin creates the illusion of heat. The cooling effect is enhanced by menthol's ability to suppress warm receptors simultaneously, creating a more pronounced overall cooling sensation. Interestingly, the body adapts to repeated exposure by temporarily reducing receptor sensitivity, which explains why the second piece of mint gum often feels less intensely cooling than the first. This chemical mimicry of temperature has made menthol a valuable ingredient not just in foods, but in topical pain relievers, where the cooling sensation provides a counter-irritant effect that masks underlying pain signals. The paradox of why we enjoy painful sensations from spicy foods has both physiological and psychological explanations. When capsaicin binds to TRPV1 pain receptors, the body responds by releasing endorphins, natural opioid compounds that create a mild euphoric effect. This pain-pleasure cycle creates what researchers call benign masochism, the enjoyment of experiences that the body initially interprets as threatening but cognitively recognizes as safe. This recognition makes the endorphin release a reward rather than a survival response. Additionally, repeated exposure leads to desensitization of pain receptors, allowing spice enthusiasts to gradually increase heat levels to maintain the same hedonic reward. Cultural and social factors also play crucial roles in spice appreciation. In many societies, tolerating extreme spice becomes associated with bravery or culinary sophistication. Research shows that sensation-seeking personality traits correlate positively with preference for spicy foods, suggesting that the controlled risk represented by capsaicin consumption appeals particularly to individuals who enjoy novel and intense sensory experiences. Nutrition science revelations: the hidden science of what you eat. Cooking transforms not just the taste and texture of foods, but also their nutritional profiles in complex ways. Heat breaks down cell walls in plants, often releasing nutrients that would otherwise remain locked away. Tomatoes offer a perfect example. Cooking increases the bioavailability of lycopene by up to 400%, as heat converts this antioxidant from its trans form to the more easily absorbed cis configuration. Yet this same process can significantly reduce water-soluble vitamins like vitamin C and most B vitamins, which are sensitive to heat, water, and oxygen exposure. Steaming vegetables rather than boiling can preserve up to 90% more of these delicate nutrients by minimizing water contact. Meanwhile, other compounds like beta-carotene in carrots and sweet potatoes actually become more bioavailable when cooked with a small amount of fat, as these fat-soluble compounds need lipids for optimal absorption. This nutritional balancing act reminds us that no single cooking method optimizes all nutrients simultaneously. The antioxidant story is more nuanced than marketing often suggests. While these compounds do neutralize free radicals in test tubes, their actions within the human body follow more complex pathways. Many plant antioxidants like polyphenols appear to work indirectly. Rather than acting as antioxidants themselves, they trigger the body's own antioxidant defense systems through a process called hormesis, essentially creating a mild stress response that strengthens cellular resilience. Additionally, antioxidants work synergistically. Isolated supplements rarely show the same benefits as whole foods where hundreds of compounds work together. The vibrant colors of fruits and vegetables, from the deep purple of berries to the rich red of tomatoes, signal their antioxidant content, as these pigments often double as protective compounds. However, antioxidants can sometimes interfere with beneficial physiological processes, as certain free radicals play essential roles in immune function and exercise adaptation, explaining why high-dose antioxidant supplements sometimes show neutral or even negative effects in clinical studies. Food synergies reveal how certain nutrients enhance each other's absorption and effectiveness when consumed together. Iron from plant sources is poorly absorbed alone, but pairing it with vitamin C-rich foods can increase absorption by up to 6 times by converting iron to its more bioavailable form. Similarly, the curcumin in turmeric shows limited absorption when consumed alone, but combining it with black pepper increases bioavailability by 2,000% thanks to piperine, which inhibits liver enzymes that would otherwise quickly metabolize curcumin. Fat-soluble vitamins A, D, E, and K require dietary fat for proper absorption, explaining why traditional food pairings like olive oil on salads or butter on vegetables evolved not just for flavor, but also for optimized nutrition. These synergistic relationships explain why whole food diets consistently outperform nutrient-by-nutrient approaches to nutrition in research studies. Our bodies evolved to process food combinations rather than isolated nutrients. Your gut microbiome, the ecosystem of trillions of bacteria, fungi, and other microorganisms living in your digestive tract, fundamentally alters how you process different foods. These microbes ferment indigestible fiber to produce short-chain fatty acids that nourish colon cells and regulate immune function. More surprising is their role in producing approximately 95% of your body's serotonin, linking gut health directly to mood regulation. Different bacterial species specialize in breaking down specific food compounds. Bacteroides species excel at processing protein and animal fats, while Prevotella species more efficiently ferment plant fibers and carbohydrates. This explains why sudden dietary changes often cause digestive discomfort. Your microbial community needs time to shift its composition to match your new eating pattern. Research increasingly suggests that individual differences in microbiome composition help explain why identical meals produce different glycemic responses in different people, moving us toward more personalized nutrition approaches based on an individual's unique microbial fingerprint. Dietary fiber extends far beyond merely promoting regularity. It serves as the primary food source for beneficial gut bacteria. Fermentable fibers like inulin, pectin, and resistant starch function as prebiotics, selectively feeding beneficial bacterial species that produce short-chain fatty acids such as butyrate. These compounds reduce inflammation, strengthen the intestinal barrier, and may even influence brain function through the gut-brain axis. Soluble fiber forms gel-like substances that slow digestion and glucose absorption, explaining its ability to stabilize blood sugar and reduce cholesterol levels. Meanwhile, insoluble fiber adds bulk to stool and speeds transit time through the digestive tract, reducing exposure to potential carcinogens. The diversity of fiber types in whole plant foods, from the beta-glucans in oats to the lignins in seeds, supports diverse microbial communities, which research increasingly links to better health outcomes. This explains why fiber supplements rarely show the same broad benefits as fiber-rich whole foods, which provide a complex spectrum of different fiber types. Fermented foods represent one of humanity's oldest food preservation methods and, coincidentally, one of our most powerful dietary tools for microbiome support. During fermentation, beneficial microorganisms convert sugars and starches into acids, alcohols, and gases, transforming both the food's flavor profile and its nutritional properties. Yogurt, kefir, kimchi, sauerkraut, kombucha, and other fermented foods introduce transient beneficial microbes that, while not permanently colonizing the gut, interact with resident bacteria and modulate immune responses. Beyond supplying beneficial microbes, fermentation pre-digests certain compounds, often increasing nutrient bioavailability. For example, fermentation breaks down phytic acid in grains and legumes, increasing mineral absorption, and creates new bioactive peptides with anti-inflammatory and antioxidant properties. Recent clinical research shows that diverse fermented food consumption increases microbial diversity and reduces inflammatory markers even more effectively than high-fiber diets, suggesting these traditional foods deserve their reputation as health-promoting culinary traditions. Dietary fats exhibit remarkably diverse effects on health depending on their molecular structure. Saturated fats, found predominantly in animal products and tropical oils, have straight molecular chains that pack tightly together, explaining their solid state at room temperature. These structural properties affect how they interact with cell membranes and cholesterol transport, though their health effects appear more nuanced than once thought, particularly when consumed within minimally processed foods. Monounsaturated fats, abundant in olive oil and avocados, contain one double bond that creates a kink in their molecular structure, preventing tight packing and keeping them liquid at room temperature. This configuration makes them more chemically stable during cooking and less prone to oxidation. Polyunsaturated fats, including omega-3 and omega-6 fatty acids, contain multiple double bonds, making them the most flexible but also most vulnerable to oxidation. The body cannot synthesize essential fatty acids like alpha-linolenic acid, omega-3, and linoleic acid, omega-6, requiring dietary sources. The ratio between these fatty acid families affects inflammatory pathways, explaining why traditional diets with balanced omega-3 to omega-6 ratios correlate with lower inflammation levels. Artificial sweeteners create their sweet taste by binding to the same taste receptors as sugar, but their metabolic effects differ dramatically. Unlike sugar, most artificial sweeteners pass through the digestive system without being metabolized for energy, explaining their zero-calorie status. However, emerging research suggests they may still influence metabolism through unexpected pathways. When sweet taste receptors in the mouth detect sweetness, the body initiates insulin release in anticipation of glucose, a preparatory response called cephalic phase insulin release. When actual glucose doesn't arrive, this may potentially contribute to altered glucose metabolism over time. Additionally, some artificial sweeteners appear to alter gut microbiome composition in ways that could influence glucose tolerance. Interestingly, different sweeteners follow distinct metabolic pathways. Aspartame breaks down into phenylalanine, aspartic acid, and methanol during digestion, while sucralose passes largely intact through the digestive system. Stevia, derived from plant leaves, works through different sweet receptor mechanisms than artificial options, potentially explaining its different physiological effects. These emerging findings remind us that calorie-free doesn't necessarily mean metabolically inactive. Culinary myths debunked, separating food facts from fiction. The belief that searing meat seals in juices has persisted since the 1800s when it was proposed by German chemist Justus von Liebig, despite being conclusively disproven. Careful measurements show that seared meat actually loses slightly more moisture than meat cooked at lower temperatures. The real value of searing comes from the Maillard reaction, the complex chemical interaction between amino acids and reducing sugars that creates hundreds of new flavor compounds and the characteristic brown crust. This reaction, which occurs most efficiently above 300 degrees Fahrenheit, 149 degrees Celsius, transforms relatively simple raw meat flavors into the complex taste profile we associate with properly cooked meats. The superior eating experience of seared meat comes not from moisture retention, but from this flavor development and textural contrast between the exterior and interior. The misconception persists, partly because properly rested meat after cooking does retain juices better than meat cut immediately, but this resting effect is independent of searing and results from cooling-induced reabsorption of liquid by protein structures. The raw food versus cooked vegetable debate oversimplifies a nuanced nutritional landscape. While cooking can reduce heat-sensitive nutrients like vitamin C and some B vitamins, it simultaneously increases the bioavailability of others. For example, lycopene in tomatoes becomes up to 5 times more bioavailable when cooked, and the carotenoids in carrots become more accessible. Cooking also neutralizes certain anti-nutrients like oxalates, phytates, and some enzyme inhibitors that can interfere with mineral absorption. Additionally, many plant foods contain compounds that are indigestible or even potentially harmful when raw. Legumes contain lectins that are deactivated by cooking, and certain starches become digestible only after heat breaks down their crystalline structure. The truth is that a combination of raw and cooked vegetables provides the most comprehensive nutritional profile, as each preparation method preserves different beneficial compounds. This balanced approach explains why traditional diets worldwide typically include both raw and cooked plant foods rather than exclusively favoring either preparation method. The persistent belief that microwaving destroys significantly more nutrients than other cooking methods is contradicted by scientific evidence. Microwave cooking often preserves nutrients better than conventional methods, precisely because of its cooking mechanism and typically shorter cooking times. Microwaves primarily cook food by exciting water molecules, heating food quickly and with less water than boiling or simmering. Since many vitamins are water-soluble, cooking methods that use less water and shorter cooking times generally retain more nutrients. Research comparing cooking methods shows that microwaving broccoli preserves more vitamin C than boiling, and microwaved spinach retains more folate. The misconception likely stems from early concerns about microwave safety that were subsequently disproven but left a lasting impression. Additionally, the rapid adoption of microwave cooking for processed convenience foods created an association between microwaving and unhealthy eating, though this reflects food choices rather than the cooking technology itself. Microwaves do create somewhat uneven heating patterns, which is a legitimate culinary limitation but unrelated to nutritional quality. Food cravings involve complex neurobiological mechanisms far beyond simple nutritional deficiencies. While folklore suggests that chocolate cravings indicate magnesium deficiency or meat cravings signal protein needs, research shows cravings more often reflect psychological, cultural, and hedonic factors. Brain imaging studies reveal that viewing images of highly craved foods activates the same reward pathways involved in substance addiction, including the nucleus accumbens and ventral tegmental area. Hormonal fluctuations explain some craving patterns. Chocolate cravings peak during the luteal phase of the menstrual cycle when serotonin levels naturally decrease, as cocoa compounds can boost serotonin. Cultural conditioning strongly influences which foods become common craving targets. Chocolate dominates in Western countries, while rice may be more commonly craved in Asian cultures. The powerful memory associations with comfort foods explain why we often crave foods from childhood during times of stress. Rather than signaling specific nutrient needs, most cravings represent the brain's learned associations between certain foods and the pleasure or comfort they provided in past experiences, essentially creating reward prediction signals that motivate us to seek these foods again. The tongue map, showing distinct taste regions, sweet at the tip, salty and sour on the sides, and bitter at the back, remains one of the most widely taught yet completely incorrect concepts in food science. This misconception originated from a mistranslation of a 1901 German paper that suggested slight sensitivity differences across the tongue. Modern research conclusively demonstrates that all taste receptors are distributed across the entire tongue, though with subtle variations in density. All areas of the tongue can detect all 5 basic tastes: sweet, sour, salty, bitter, and umami. Differences in perception often attributed to tongue regions actually result from other factors, like the volatility of flavor compounds, saliva flow patterns, and temperature gradients in the mouth. This correction highlights how scientific misunderstandings can persist in popular culture and education long after being disproven by research. The actual distribution of taste receptors does show some specialization, but at the cellular, rather than regional level, different receptor cells respond to different taste qualities regardless of their position on the tongue. The concern that spicy foods physically damage taste buds reflects a misunderstanding of how capsicum, the active compound in chili peppers, interacts with our sensory system. Capsicum doesn't actually burn or damage tissue at normal dietary concentrations. Instead, it activates TRPV1 receptors that normally detect actual heat, creating the perception of burning without causing actual thermal damage. While extremely concentrated capsaicin, as in pepper spray, can cause inflammation, the levels in even the spiciest foods don't physically destroy taste receptors. What does occur is temporary desensitization. Repeated exposure to capsaicin causes receptors to become less responsive, explaining why chili enthusiasts can tolerate increasingly spicy foods over time. This adaptation is reversible and represents a normal neurological response rather than damage. In fact, research suggests moderate capsaicin consumption may have protective effects for taste buds by increasing blood flow to oral tissues and through its antimicrobial properties. The burning sensation of spicy foods triggers endorphin release, creating the distinctive pleasure-pain response that makes spicy food enjoyable rather than simply painful for regular consumers. Understanding food science fundamentally transforms cooking from a process of following recipes to one of confident culinary improvisation. When you grasp that browning meat develops flavor through the Maillard reaction rather than sealing in juices, you become free to sear when appropriate for flavor development and skip this step when time or other factors make it impractical. Knowing that salt enhances flavor not only through saltiness, but by suppressing bitterness and releasing volatile aroma compounds allows you to use it strategically throughout the cooking process. Understanding the chemistry behind thickening agents, from flour's starch gelatinization to the protein coagulation in egg yolks, empowers you to troubleshoot when sauces break or fail to thicken properly. This knowledge transforms cooking from mysterious successes and failures into a series of predictable, controllable reactions, ultimately making cooking both more reliable and more creative. Food science continues to evolve as new research techniques reveal previously hidden aspects of how we experience food. Recent advances in brain imaging have revolutionized our understanding of how flavor perception integrates information from multiple senses simultaneously. The emerging field of nutrigenomics explores how individual genetic differences influence our response to various foods and nutrients, moving us toward truly personalized nutrition. Ongoing microbiome research reveals the profound influence of gut bacteria on everything from mental health to immune function, potentially explaining why dietary effects vary so significantly between individuals. As analytical techniques become more sensitive, we continue to discover new bioactive compounds in familiar foods, polyphenols, peptides, and other micronutrients with potential health effects beyond basic nutrition. These frontiers remind us that despite centuries of culinary tradition and decades of food science research, we are still uncovering the full complexity of our relationship with food. The intersection of science and culinary arts offers endless opportunities for exploration, whether you're a curious home cook or a professional chef. I encourage you to approach your kitchen as both laboratory and studio, a place for experimentation guided by scientific principles but expressed through creative intuition. Try the simple experiments we've discussed. Compare the flavor of refrigerated versus room temperature fruit to experience temperature's effect on sweetness perception. Taste foods while pinching your nose to isolate true taste from retronasal olfaction. Pay attention to how texture influences your perception of identical flavors. These personal experiences transform abstract scientific concepts into tangible culinary knowledge. Remember that cooking represents one of humanity's oldest technologies, the controlled application of heat, fermentation, and other processes to make food more nutritious, delicious, and safe. By understanding the science behind these transformations, you honor this ancient tradition while continuously innovating. The kitchen remains one of the few places where science, art, culture, and personal expression converge in daily life, a truly interdisciplinary adventure that nourishes both body and mind.